Good afternoon, everyone. Now is the time for part 10, the final section of the notes, final section of the material for this class this semester. This part is on rotational dynamics. Part 9 was all about rotational kinematics, so describing the rotational motion of objects. Here we're going to explain why those objects rotate. The first thing we need to do is look at the torque. The torque is the equivalent in rotation to the force. So we have a couple of different quantities that are linked together or can be linked rotational to linear. So in linear motion, in rotational motion, for example, we had from linear to rotational, we had position, we had the velocity, we had the acceleration, we had the mass, and the moment of inertia. These two here were the initial properties of the object, so how hard it is, how difficult the object is to either make linearly move or angularly move. Then we had the linear and rotational kinetic energies, given by 1/2 mv squared or 1/2 I omega squared. The equivalent for the torque is the force. Both are vectors, so they would need to be written with an arrowhead on top of them. Loosely defined, a torque is the quantity that causes an object to rotate. It depends on the force that's being applied, but also where it's applied and of course, in what direction. For example, this marker is static, besides the slight shake of coffee. Because of my fingers here, I'm determining this to be what's called a pivot point, through which the axis of rotation goes. So we have, for example, the x direction, y direction, z direction towards you. If I put my finger here, for example, right at the edge of the cap and the marker, and I push that way, this happens. Of course, I started pushing horizontally and I ended up pushing vertically at the end. I went through an arc of a circle. But what happens exactly at this moment, exactly when I touch and start pushing, is I apply a torque. I apply a force at some distance from the pivot point, from the axis of rotation. That creates a torque. It causes an object to rotate. You do that every day. Every time you open a door, when you push or pull on the handle, you apply a torque to that door, and that door rotates about the hinges. It's exactly the same. The mathematical definition of the torque. The torque, tau, the Greek letter for t, is the cross product in between r and f, the position vector of the force F. We have here in red the position vector r. It determines the place on the object from the axis of rotation where the force is being applied. It can be applied anywhere and in whatever direction, but in this case it is applied exactly here. And there's an angle in between these two vectors. That's this angle phi here. This is a cross product. It's the multiplication of two vectors that gives a third vector at an angle that is 90 degrees from both initial vectors, in this case both r and f. We will usually worry about finding the magnitude of the torque. And to do that, we simply use this. We need to take the magnitude of r, the magnitude of f, and the sine of the angle phi in between these two vectors. This will give us the magnitude of the torque. By using the right-hand rule of cross products, we can determine the direction of the torque. To do that, what we'll do is we'll align our fingers in the direction of the first vector, always r, and we'll curl them, we'll close our hands in the direction, so coming from this direction to the vector, where does the second vector, the f vector, go? In this case, r curl towards f, the thumb extends in some direction. In our case, the thumb extends into the board, so the torque would be considered negative. It goes along the negative z direction. X, y, and positive z. The torque points into the board towards the negative z. You can think of it also this way. We define a positive rotation to be counterclockwise. This force would create a clockwise rotation. Therefore, the torque is negative. We will worry about the direction and the magnitude kind of separately, much like we did in linear dynamics, where we looked at the components of every force and we established whether they were positive or negative by sketching things out on a free body diagram. We'll do something very similar. That's the definition of a torque. In linear motion, we had determined the work to be the product in between the force and the displacement. And we assumed for our purposes that the displacement was always linear along one dimension and the force was constant. In this case, in rotation, we have an angular displacement, just a rotation, and a torque that's being applied. The work done by a torque to cause a rotation is given to us by Tau is the torque still that we can find, and delta theta is the angular displacement of the object while that torque is being applied. Note here the difference in angle. Theta here is the general variable for the angular position and delta theta for the angular displacement with respect to the positive x-axis or the starting point of the whole object. Phi here will reserve for the angle in between the two vectors r and f. We'll need to be careful about those two angles, and sometimes we might need to use other letters such as beta, gamma, delta, and other Greek letters to symbolize different angles if we need to. That's essentially it for the work in torque. Oh, I forgot to mention that the units for the torque you can find by multiplying the units for distance and force, so they would be Newton times meters and not meters times Newton, because we could confuse those with millinewtons. You can see why.